I always find number theory to be so interesting and these algorithms to be quite a bit of fun because we're dealing with a lot of arithmetic, and the unique ways in which we pass numbers back and forth can actually create some positive results. And this is one of them. The extended Euclidean algorithm, which is again something that we're going to need soon, is sort of using the Euclidean algorithm and then working it in reverse to come up with an important result. I do not know how to say this individual's name, but I believe it's Bézout. Bézout's theorem states that if A and B are positive integers, then there exist integers s and t. So that means that you can find integers s and t such that the greatest common divisor between A and B is equal to some multiple of A plus some other integer multiple of B. Now the key here is when we look at a theorem like this, we have to look at the conditions. The conditions state that first of all, A and B are positive integers. Then there exist integers s and t. Now these could be positive or negative. There's no specification in this theorem, but A and B, the two values that we're looking at the GCD between, have to be positive. Okay, so we can already see that this has something to do with the greatest common divisor, and therefore the Euclidean algorithm could in some way help us formulate this. Let's take a look at the GCD between two smaller numbers to begin simulating this process. So let's say we want to find the GCD between, we'll say, I don't know, I'm feeling like maybe 10 and 6. So 10 and 6. Now, it doesn't matter what order these numbers are listed in. I'm always going to pick A to be the larger of the two values. So in this case, I'm going to say A is 10 and B is 6. You can do it with A equals 6 and B equals 10, but it's just more consistent if we allow A to be the larger number. So what we know about the Euclidean algorithm is that if you can write a number as A equals B times some quotient plus some remainder, then it follows that the GCD between A and B is the same as the GCD between B and R. And in this case, our A is 10, and we want to know how many times does 6, our value of B, go into 10? Well, it goes into 10 one time and leaves a remainder of 4. Now, according to this statement, the GCD between these two numbers is the same as the GCD between these two numbers, so I'm going to focus on those. And now I'll say 6 equals how many multiples of 4? Well, 4 goes into 6 one time, leaves a remainder of 2. And now I can say that the GCD between 10 and 6 is the same as the GCD between 6 and 4, which is the same as the GCD between 4 and 2. So my next line will involve 4 is equal to 2. And how many times does 2 go into 4? Well, it goes in 2 times, leaves a remainder of 0. And so we have our GCD, which is 2. So the GCD between these two numbers is 2. And what we're saying is that we can take some multiple of 6 and some multiple of 10, add them together, and arrive at the value of 2. So this process of the extended Euclidean algorithm really just works backwards. It works from what we would normally call, at this point, step 3. This is just sort of our termination line. This is where the algorithm terminates. And any computer will know by the remainder of 0 that the algorithm has concluded, and that the previous remainder, in this case 2, is the GCD. So we're going to start with this line, work our way back up to this line. So step 1, I see that 6 is equal to 4 times 1 plus 2. Now in each of these lines, the two numbers that I'm dealing with are, in this case, 6 and 4, 10 and 6. And that's going to be key in underlining or highlighting the values of A and B, because we're going to work backwards to express 2 as a function of our original values, 10 and 6. All right, so since 6 equals 4 times 1 plus 2, if we, it's natural to want to just say, well, 6 equals 6, and that's a true statement. But if I write 6 and subtract away 4 times 1, that's equal to 2. And already I see that my GCD is equal to some combination of 6 and 4. Now, the reason I focused on 6 and 4 is because in this step, I'm going to be focusing on 6 and on 4. From our last step, we see that 4 is actually a function of 10 and 6. So what I'm going to do in this next step is I'm going to realize that and use step 2 to indicate that 10 is equal to 6 times 1 plus 4, and therefore 4 is equal to 10 minus 6 times 1. Now notice that I'm not combining these values. I'm not leaving it as 4 equals 4. Instead, what I'm going to do is I'm going to take this 4 and I'm going to replace it in this equation right here. And the reason I'm going to do that is because what I want to do is work backwards so that my equation is only a function of the 10 and the 6. All right, so to conduct that step, we are going to take this expression right here, 6 minus, now 4 is equal to 10 minus 6 times 1, and that's being multiplied by 1. And I know that that equals 2, because all I've done is just created a substitution there. And now I want to focus my attention on 6 and 10. More specifically, I want to keep track of how many 10s and how many 6s there are in there, and then how those two expressions of 10 and 6s are being combined. So I'm going to leave this as 6. Now I can distribute this, there's a negative 1 there, so I have negative 1 multiples of 10. And then I have negative 1 times negative 6 is positive 6 multiples of 1, or alternatively, 1 multiple of 6. And that's all multiplied by 1, so the answer would not be changed by that. Now here I have 1 multiple of 6, and here I have 1 multiple of 6. So if I have 1 multiple of 6 and another multiple of 6, I have 2 multiples of 6, and then I have negative 1 multiples of 10, and I see that by substitution this should still equal 2. In fact, 12 minus 10 is indeed 2. The theorem states that there exists some multiple of A plus some multiple of B such that you equate to the greatest common divisor. And we have that. 2 is the GCD, so I'll write this as 2 equals 2 times 6 minus or plus negative 1 times 10. This was my value of A. This was my value of B. So if I want to keep it in the order of A and then B, I could say I have negative 1 copy of 10, plus I have 2 more copies of 6, and now I've satisfied the theorem. 2 is my GCD between 10 and 6. Again, the order in which the values are listed does not really matter. And that is equal to S times my A value. So this is my S, this is my A, plus some multiple of my B value. And we have effectively shown, at least for this instance, that Bézout's theorem does in fact hold by working the Euclidean algorithm in reverse. Now this will work for any two values, and we can kind of see why, because the back substitution process allows me to get back to my original two values A and B, 10 and 6, via these substitutions. Let's go ahead and take a look at another example. The GCD between 24 and, we'll say, 16. Okay, so 24 can be written as 1 multiple of 16, and that leaves a remainder of 8. So the GCD between these two is the same as the GCD between these two, and now I'm going to focus my attention on 16 and 8. And 8 goes into 16 2 times, leaving a remainder of 0, and therefore I can say that my greatest common divisor is 8. via this back substitution process, I want to be able to say 8 equals some multiple of 24 plus some multiple of 16. And the way in which I will do that is I will start at the step where I've identified my GCD, and in this case it's a little bit easier to see. Here, the step before our termination step says that 24 is equal to 16 times 1 plus 8. And if in this equation I already see that what I'm keeping track of here is the A and the B, I want to keep track of how many 24s and 16s there are going to be, then I can rewrite this as 8 is equal to 24 minus 16 times 1. And to clean this up and make it look more like this equation, I already see that 24 and 16 are here, but I will write this as 1 times 24 plus negative 1 times 16, and I have effectively identified my S and my T values. This could carry on for multiple steps, where maybe we want to take something like the GCD between 25 and, we'll say, 15. So for 25 and 15, we can say 25 is equal to 1 multiple of 15 plus 10. Now I'm going to focus on the GCD between these three values. So 15 is equal to 10 times 1 with a remainder of 5. GCD between these two is the same as the GCD between these two. And so 10 is equal to 2 multiples of 5 with a remainder of 0. Now at this point I have identified the GCD as being equal to 5, and what I can do next is use back substitution to achieve an equation that relates 5 in terms of my original two values, 15 and 25. So in each step, what I'm going to be focusing on are the two values of A and B. So what I want to do first is equation 1 will allow me to write 5 is equal to 15 minus 10 times 1. I don't want to change the 10 and I don't want to change the 15 because my ultimate goal is to express 5 in terms of 25 and 15. So in the next step, I'm going to focus on keeping track of the 15 and the 25. So what am I going to substitute out? Well, I'm going to substitute the remainder out in each step. So this 10 right here, according to equation 2, tells me that 10 is replaceable with 25 minus 15 times 1. So I'm going to want to keep track of the 15 and the 25s. Okay, so in this equation we can now say that 5 is equal to 15 minus, now I'm going to replace 10 with 25 minus 15 times 1. And that's being multiplied by 1, so that's not going to change the effect of it. But if I reduce this a little bit more, I can say 15, this is a negative 1 here, so I can say minus 1 copy of 25 plus 15 times 1, or plus 1 copy of 15, is equal to 5. And we can just double check this. 15 minus 25 is negative 10. Negative 10 plus 15 is 5. So I'm just going to rewrite this. Again, I just want to be very careful that I'm keeping track of the number of 15s and the number of 25s that I have. And I see that I have negative 1 copy of 25, my value of A. And I have 1 copy of 15 here, 1 copy of 15 there. So I have 2 copies of 15. And once again, I've been able to express my GCD as some integer multiple of A plus some integer multiple of B. And according to the theorem, the multiples themselves, the S and the T values, do not need to be positive. One of them could be negative, or well, they can't both be negative, because in that case our GCD would be a negative value. Let's take a look at one more where there are additional steps beyond just this. We'll focus on the GCD between 296 and 124. So as a refresher, to create or locate this GCD, we're going to figure out how many times 124 goes into 296, and it goes into it 2 times. That creates 148, and 248, and 296 minus 148 is 48, so that leaves a remainder of 48. We know that the GCD between 296 and 124 is the same as between 124 and 48. And so 48 goes into 124 2 times, leaving us with a remainder of 28. Next, we'll go ahead and focus on 48 and 28. And 28 goes into 48 1 time, leaving a remainder of 20. And now we can focus on 28 and 20. 20 goes into 28 1 time, leaves a remainder of 8. And next we can look at the GCD between 20 and 8. 8 goes into 20 2 times, leaving a remainder of 4. In our final step, 8 is 2 multiples of 4 plus a remainder of 0, and so we know that our GCD is 4. So I have 1, 2, 3, 4, and 5 equations here that are going to need to be rewritten. Now what I'm going to go ahead and do to make our life a little bit easier is each time I'm going to be replacing the remainder in the next step is going to replace the remainder in the previous step. So 8 is going to replace 8 here. This 20 is going to replace this 20. This 28 is going to replace this 28. And this 48 is going to replace this 48. So what I'm going to go ahead and do is I'm going to create a series of equations here that express the remainder in terms of the rest. Now in step 1, that's our GCD equation. So 4 is equal to 20 minus 8 times 2. Now better yet, I'm going to write that as negative 2 copies of 8. Because what I want to keep track of are the values of A and B within each step. So the second equation can be rewritten for the remainder as 8 is equal to 28 minus 1 copy of 20. And the third equation allows me to write 20 is equal to 48 minus 1 copy of 28. So again, what I'm really doing here is just keeping track of the 48 and the 28. In equation 4, we're going to keep track of the 124 and the 48. So 28 is equal to 124 minus 2 copies of the 48. And in equation 5, I'm going to express 48 in terms of 296 and 124. So 48 is equal to 296 minus 2 copies of 124. And so herein lies my back substitution. So I'm going to replace the 48 here with the 48 down here. This 48 is going to replace this 48. This 28 is going to replace this 28. This 20 is going to replace this 20. And then finally, this 8 is going to replace this 8. So let's go ahead and do that. If I make my first substitution, 4 is equal to 20 minus 2 times 8, and 8 is equal to 28 minus 1 copy of 20. Again, in this step, I can see that I'm keeping track of the 20 and the 28, so I want to make sure that those don't get canceled out. So I have 4 is equal to 20, negative 2 copies of 28, plus 1 copy of, plus 2 copies of 20. And that can be simplified down to saying, well, here I have 1 copy of 20. Here I have 2 more copies of 20, so I have 3 copies of 20 and negative 2 copies of 28. Now we should just be able to check our work here. 3 times 20 is 60. 60 minus 56 is 4, and so that still gives me the correct value. So that checks that checks off of our list this substitution here. Next, we're going to go ahead and replace 20 with 48 minus 1 times 28. So we have 4 equals, and then we're focusing on this reduction right over here. So 20 is equal to 48 minus 1 copy of 28. And then I have minus 2 copies of 28. So in this step, remember, we want to keep track of the 20 and the 28. So I can further reduce this. I can say I have 3 copies of 48 distributing, minus 3 copies of 28, and then I have minus 2 copies of 28 here. So I can say that 4 is equal to, well, I have 3 copies of 48, and I have negative 3 and negative 2 more copies of 28, so I have negative 5 copies of 28. And again, I should just be able to check my arithmetic, that 3 times 48 minus 5 times 28 is equal to 4. That takes care of our substitution in step 3. Now I'm going to replace the 28 with the expression that it is equal to. So I will write 4 is equal to 3 times 48 minus 5 times 28, but wait, 28 is equal to 124 minus 2 copies of 48. And in this step, I'm going to focus on the 28 and the 48, because ultimately I want to focus on the 296 and the 124, my original 2 values of A and B. So this can be reduced to 3 times 48 minus 5 copies of 124 plus 10 copies of 48, and that can be reduced to, I have 13 copies of 48, negative 5 copies of 124. And I'm close, because I see that I have a 124 in my equation. I just need to get that 296 in there, and that 296 is going to be introduced by substituting out the 48. So I am going to write 4 is equal to 13 times 48, but 48 is equal to 296 minus 2 copies of 124, and then I have the minus 5 times 124. Awesome. Okay, so here we are. We have 4 equals 13 copies of 296. 13 times negative 2 is negative 26 copies of 124. And then I have minus 5 copies of 124. And now we can see that 4 is a function of 296 and 124. So I'm just going to go ahead and collect those. I have a total of 13 copies of 296, and I have negative 31 copies of 124. And so once again, the GCD between 296 and 124 is equal to some number S, which is 13, times my value of A, which is 296, and I can put a plus sign in here, plus my T value, which is this negative 31, copies of the 124. And there's another instance of a more involved process, which you can see that this could be somehow allocated to a computer to be able to do this, but nonetheless, I've been able to apply Bézout's theorem by using the Euclidean algorithm, but in the reverse order.